So today we are doing section 12.3 and section 12.4. Take a minute, copy all this down, and then I'll explain it. This says, find the sum of an infinite geometric series, for which R is less than 1. Okay, the sum of an infinite geometric series. So I got our notes that we had last time. We already did the sum. So what is this? This was actually the sum of a finite. Again, sequence, series means sum, but I use the two words interchangeably. So this was a sum of a finite number. So you guys would have a problem like, oh, find the sum of the first 60 terms. Well, that makes sense. I have 60 terms and I'm going to find the sum of them. But what happens when you have an infinite sum? If you have an infinite set of numbers and it's infinite, how can you find a sum? That doesn't quite make sense. So let's think about this. If you have an infinite series, let's just take a simple series. Let's see if this works. Okay, if you have 1 doubled, 2, 4, 8, 16. If I have this series and it goes on and on and on and on forever and ever and ever and ever, how can I have a sum? Actually, this sequence is growing and growing, and this is actually called a divergent sequence because it gets bigger and bigger and bigger and bigger, and it'll never end, so it's called divergent. Okay? Again, don't write any of this down, just kind of listen. Let's see if this part works. Now, so we know that this sequence is geometric and it's divergent because it gets bigger and bigger and bigger and it never ends. Eventually, you would have so many. Let's look at another sequence and see if we could also infinite. I have one Post-it. I'm going to take that one Post-it and I'm going to cut it in half. So I'm going to add half. So now I have 1 plus a 1/2. I'm going to take that half, cut it in half. So now I have a 1/4. I'm going to take the 1/4, cut it in half. And I'm going to keep going. What's half of 1/4? I'm going to take 1/8, cut it in half. Actually, I'm going to rearrange this one this way. Take 1/16, cut it in half. You get the idea. I have 1/32, cut it in half, 1/64. Now, if I continue this sequence, and I keep cutting these pieces smaller and smaller and smaller and smaller, I can go on forever and ever and ever. What is the sum of this series going to be? It's actually going to be 2 Post-its. So there's a rule, and this actually jumps over to section 12.4, and I'll come back to it. There's a rule that says, and I'm really oversimplifying it. If you look at your book, this rule is actually pretty complicated and it has a lot of different things. I'm just going to make it really simple and say, look, if you have an arithmetic sequence, remember arithmetic is adding or subtracting, that's always going to be divergent. So if you take 2 and you add 3 to it, 5, 8, this is just going to get bigger and bigger and bigger. So that's divergent. Same thing if you subtracted it. If you have 2 and subtract 3, -1, and then -3, -4, -7. So this is going to go to positive infinity. This will go to negative infinity. But either way, it just gets bigger and bigger and bigger, smaller and smaller. And if you were trying to find the sum of it, it's too much. So that's called divergent. always for arithmetic. If you have a geometric sequence, like we just saw, if you have a common ratio where you're multiplying by 1/2 every time, this is a divergent or convergent, because this actually approaches a number. The sum of this is going to equal 2. And you can copy this later, but I'm just explaining it now. The sum of this is going to equal 2. So that says, oh, if you have a geometric sequence and your fraction or your common ratio is a fraction, then it actually approaches a number and it becomes convergent. If your common ratio is a number greater than 1, you're multiplying by 2 here, it's just going to get bigger and bigger and bigger. And of course, you're never going to have like a final end number because it just gets bigger and bigger, either really big or really small. And it is a divergent. Okay, so that's what that means. There's other series and they have like information, but pretty much just kind of think about it. You'll only have a couple of problems on your homework for this that will have you just think about it. Again, if you didn't copy this down, no worries. I'm going to come right back to it. Okay, so let's go back to this. Okay, so you should have this copied down. Otherwise, pause and copy it down and then hit the video. So a sum of an infinite geometric series, it does exist if your common ratio is a fraction. If your common ratio is a fraction, then you're going to use this formula. The formula says it's your first term divided by 1 minus your common ratio. So let's do the first problem. In the first problem, we see that it's going here. So first you have to identify the sequence. Again, if it's arithmetic and it's an infinite, you wouldn't be able to do it. It has to be a geometric sequence for you to find the sum. So I'm going to take this and say, first I need to know my first term. Got it, 21. And I have to know my common ratio. Well, what's your common ratio? Remember, you take the second term, divide it by your first term. And you can actually multiply it to make sure that that is correct. Okay, so I have my common ratio. I'm going to use the formula. And then plug in your information. The sum of the infinite series is my first term divided by 1 minus 1/7. And you can just stick this into your calculator, get the answer. Or if you want to actually just work it out. Let me pause it and work it out. So I got my calculator, did my math. Careful. This was 21, 1 minus. Remember that this was negative 1/7. So this is minus an already negative 1/7. So make sure you include that negative right there. So it turns out to 21 over 1 1/7. So that's going to be 21 over 8/7 multiplied by the reciprocal. 21 times 7 over 8 is 147 over 8. Plugged 147 over 8 into my calculator, 18.375. 18.375 is the same thing as 18 times 8 goes into 144. So it is 18 and 3 left over. All right, 18 and 3/8. Now, if you just plugged it all in at the beginning, 21 divided by 1 minus negative 1/7, you know, it just saves you all that work. Okay, so that's your answer. And this is a 3 right there. All right, next problem. Oh, and one last thing. In this case, because your R value is less than 1, this sequence is considered convergent or divergent. Convergent, that it actually approaches a number. So this sequence is convergent. All right, let's try another one. So here, find the sum of the series. Again, I don't know how it's growing, so I'm just going to use my calculator and say, okay, to find my R value, it is my second term divided by my first term. So R equals 24 divided by 60. 0.4. So my R value is 0.4. I actually want to make sure that that is correct. So you can do this two ways. You can either take, well, 60 times 0.4, yeah, and then 24 times, so it works. Or you could have also done 9.6 divided by 24. Okay, either way. So it is correct. So I have my R value, go back to my formula. Sum of this right here is less than 1. Because it's less than 1, is this convergent or divergent? Convergent. If it's convergent, then it has an answer, as in it has a sum. We're just going to go to the formula. Formula is so the sum of the infinite series is your first term, 60. Yeah, and this formula is a lot nicer than the other formula. Divided by 1 minus 0.4. Again, plug it all into your calculator, or divided by 0.6. Your answer is 100. Let's see, 60 divided by, okay, all right, good. Next one. So first, you can probably already see what the pattern is growing, but again, if I didn't know that, I would go 6 divided by 3 is 2. Oh yeah, it looks like it's doubling. Okay, because R is 2, that means that this does not have a sum. It is divergent. You could put the sum does not exist if you want, divergent. If it's a divergent, gets bigger and bigger, or either smaller and smaller, so the sum does not exist. That's it, not too bad. All right, the next part of section 12.3 is limits. Now, I'm not going to assign you any homework on this part. I was debating against it, so I'm just going to explain it. And again, oversimplifying it because there's rules. And it's kind of neat to look at the way I explain it versus your book, because I just definitely overgeneralize. But this section is, let me find my paper, is actually the beginning of, I would say calculus. When you do calculus, they do limits. Okay. So the first part says, given this equation, tell me what the answer is going to be if n gets really, really big as n goes to infinity. So the limit as n goes to infinity of this problem. And you can kind of, there's a right way to do this. I'm going to just kind of have you guys think about it. Your book actually only has you going to infinity, but sometimes they'll have you going to negative infinity, or as it approaches the number 2, as it approaches the 0, as it approaches 3. And that's more of your calculus, but for right now, they're just introducing this. So what you're going to do is you're going to say, okay, and copy this down. You're not going to be assigned homework on this, but it is just kind of good information to know. I'm going to take this and divide it by each one. 1 over n squared plus. Reduce this. Okay. So now let's think about this. If n goes to infinity, and what I do is I just kind of think of a big number, like, oh, 1,000, a million. 1 divided by 1 million, you can't see how many zeros. Anyways, a bunch of zeros. It's going to be such a small number that it's almost like irrelevant. So we say that this goes to 0. And then you have the number 3. So the limit of this as it goes to infinity, these become negligible. So your answer is 3. It actually approaches the number 3. Next problem. And what your book, I think your book breaks it apart, but it's easier just to think about it this way. Same thing, I'm going to do this one a little bit differently. This one, it says, okay, I'm going to simplify it again. And the more you do of these, the more you can kind of just see this. So 5n squared divided by n squared plus 1 plus n divided by n squared plus 1 minus 4 divided by n squared plus 1. Okay, so I just divided this by each term, and then I'm going to kind of simplify it. Well, if n got n squared plus 1, well, let's just do this. In this case, here, -4, n squared is going to be, let's just pick 1,000 again. So if I did -4 divided by, oh, that would be 1,000 squared. So that's going to be so small. Let's see if it does the parentheses. You probably already know what that's just going to be a really small number. Okay, so this becomes irrelevant. It goes to 0. This is actually going to be the same thing. If you ignore this 1 becomes negligible. So then you have n over n squared. So it's 1 over n. 1 over n is going to be the same thing. That's just going to be a number that goes so small, so that goes to 0. Again, this 1 in the denominator is going to be irrelevant if you have an n squared. So that goes away. The n squareds cancel, so your answer is just 5. Again, this is an oversimplification, but that's kind of how I think about it. And you can see your book if you want, you know, their explanation of it. Okay, next problem. I'm going to do the same thing. Divide by the denominator. 2 divided by 2n plus. Okay, so I'm going to simplify this. This becomes 1 over n. This becomes 5/2. And this becomes, careful with this one, 2n. Okay, so I simplified this. Now, if you look at this, 1 over 1,000,000 is going to be negligible, right? That goes to 0. 5/2, you do have 5/2, but in this case, you would have 2 times 1,000,000, 2 times 1,000,000,000,000. This thing gets so big, it would just get bigger and bigger and bigger. And so we say that this one, as n goes to infinity, this just gets super big. So this is 5/2. But what's 1.5 or 2.5 plus, 3 trillion? It's negligible. So this just gets really big. So this goes to infinity. 3 trillion doubled or whatever. So we're just going to say it gets super big. Because it is very big, and you actually can't say that, it has no limit. All right, take a minute, try to guess on this one and see what you get. All right, so did you guys get an answer for this one? This one's a little bit different. I actually wrote it wrong from your book, but it doesn't matter. Let's work this one out. So this is going to say, okay, this 1 in the denominator again becomes negligible. Your n's would cancel, and you would get 1/8 as it approaches infinity. If you weren't sure and you want to get an idea, you could plug in like 1,000 or 1,000,000 or whatever. And so I just kind of quickly plugged in 1,000. If you plugged in 1,000 divided by 8 times 1,000 plus 1, you can see I get, here's my answer. And 1/8 is here. So it approaches the 1/8. Then again, you can try 1,000,000 or whatever numbers and you would see that. So again, this is just kind of an introduction. You don't have homework on this or anything, but this is good information just to kind of know how to read limits. All right, and we already did these notes, and I think you have one more set of notes. Okay, let's go through this again. Copy this down. This will be your last page of notes. If your sequence is arithmetic, meaning, and again, this is an oversimplification of all the information in your textbook on page 789. There's actual more formulas to this. If your sequence is arithmetic, is if you're adding the same thing every time or subtracting the same thing every time, it's either going to get really big or really small. So that doesn't have a sum of the infinite series. We call that divergent. In a geometric series, we know that if you are multiplying by a fraction, then your sum will approach a number and you can calculate it using the formula, and that is called convergent. If you have a geometric series and you're multiplying by a number greater than 1, it is divergent. Let's just say, yeah, okay, I won't get into anything else. And then if there's other series, or let's just say, what if R was a negative, then you're multiplying by a positive, then a negative, negative, and positive. Anyways, so we won't get into that. But other series, you can kind of just think about it. You have a couple of problems on this, and I just want you, if it's geometric, obviously you can get an answer. If it's arithmetic, same thing. If it's another series that's not arithmetic or geometric, kind of look at the pattern and see, oh, is it getting bigger in that case or smaller? That would be divergent. Or if it's approaching a number, then it would be convergent. Okay, and that's it for today.